In this video, we will be looking at how to add and subtract vectors. And both of these operations are really useful and important for certain vector applications that we will be looking at later on, like when we have different velocities or different forces acting on a single object. Now, to start with some terminology, when you add two or more vectors, we call this the resultant vector. Okay? Now, there are two different ways we can add vectors, using a parallelogram law or the triangle law, and it all depends on how your vectors are arranged. If your vectors are tail to tail, like right over here, then we have to draw a parallelogram. So draw another line parallel to vector A, another line parallel to vector B to create that parallelogram, and then your resultant vector starts at the tail of your vectors and is going to be the diagonal of the parallelogram. So this right here is your resultant vector. Now, this law here is useful because when you're given the angle between two vectors, your vectors are lined up tail to tail. So this is always useful in that scenario. Other times your vectors might be arranged head to tail. For example, the head of A with the tail of vector B. And when that happens, we can add our vectors by starting at the tail of your starting vector and ending at the head of the second vector. And this is your triangle law because the three vectors form a triangle. So we'll look at a few examples using both laws. Our first example, we have two vectors, A and B, that are 40 degrees apart, so that means that the vectors are tail to tail when our angle is given. If vector A has a magnitude of 4 and vector B has a magnitude of 5, determine the resultant vector A plus B. So I'm going to start off with a diagram. I'm going to put vector A on the bottom, and it has a magnitude of 4. And the angle between A and B is 40 degrees. So I'm just estimating here. This is vector B, and its magnitude is 5. Because my vectors are tail to tail here, I'm going to use that parallelogram law. So I'm going to draw a parallelogram from the vectors I'm already given, and my resultant vector will start at the tails, and it's going to be the diagonal. So this is vector A plus B. And now we are ready to solve. We just have to fill in some missing information. So first of all, the side across from 5 is also 5. The side across from 4 is also 4. And we just need another angle. All 4 angles in a parallelogram add up to 360. And the ones across from each other are equal. So this is also 40, and these two match. So if we know all 4 angles add up to 360, then these two angles here have to add up to 180 because the other side angles match. So this is 40 and this matches this one. So they both have to add up to 180, which means this one here is just going to be 180 subtract 40, which is 140 degrees. And now we have the perfect scenario to do a cosine law because we have two sides and the contained angle to find the magnitude of vector A plus B. So my magnitude is going to be, and normally it would be c squared, but I'm just going to go straight to square rooting the two sides squared minus double the two sides and cos of the contained angle. And then I'll just clean this up, punch it into my calculator. get approximately 8.46 units. Okay, I could round to 1 or 2 units. I didn't specify, so 8.46 is good. And now that we have that length, that has opened up a full pair for us between the 140 and this side length here, which is going to help me do a sine law to solve for my direction. So I'm going to solve for this angle here. I'm going to just label it theta, and now I'll do a sine law. So the 8.46 matches up with the 140, so sine 140, and then the 5 is across from theta, so 5 over sine theta, and now I can cross multiply. So 8.46 times sine theta equals 5 times sine 140. And then I'll divide both sides by 8.46. And I will take the sine inverse of this entire fraction to get my actual angle. And when I do that, I get 27 degrees. So my magnitude is 8.46, and the direction of the resultant vector is 27 degrees above vector A. Of 8.46 units, 27 degrees above vector A. So we draw our diagram, and then we're back to using those grade 10 sine law, cosine law, or SOHCAHTOA if our vectors were set up in a way that their angles were 90 degrees. Now, a little property about the magnitude of the resultant vector. The resultant vector magnitude is always going to be less than or equal to the sum of your starting two vectors. So in the previous example, 4 and 5 were my starting vectors. The sum of 4 and 5 is 9. The resultant vector has to be 9 or less, which we got a number less than that. That's perfect. The only time that the magnitude will be equal to the sum is when the two vectors are in the same direction. For example, if this had been vector A and this had been vector B, so this was 4, this was 5, then my resultant vector would be 9 because the original vectors were going in the same direction, so we're just adding those values. That's the only time it would be equal. Now I have two vectors here, A and B. We're going to draw the sum of A plus B, and then we'll draw the sum of B plus A. And I'm going to use the triangle law in this case. So I'm going to set up my vectors head to tail. And if I'm doing A plus B first, I'll draw vector A, and then I'll draw vector B at the head. Here we are. And using our triangle law, we have to start at the tail of A and end at the head of B. That is A plus B. Now I'll do it the other way around. So I'll start with vector B, and I'll add on vector A at its head. And here's the resultant, B plus A. These are the same thing if you look at the resultant vectors. I didn't draw them perfectly the same, but they are the same. So it doesn't matter in which order you add vectors, you will still get the same resultant. This leads us into the commutative property of vector addition. So if you add 3 or more vectors, we can place them all head to tail so that the tail of the second vector is at the head of the first vector, like I did in the previous example. But then if I'm adding another vector onto that, I'll put that third vector, its tail, at the head of the second, and so on. So I can add lots and lots of vectors, and as long as I'm setting them all up head to tail, my resultant vector will start at the tail of the first and end at the head of the final vector. So let's look at this example here. I'm adding vector A plus B plus C plus D, and they're all arranged head to tail if you look at the ends here. So that means my resultant vector will start at A and end at E, and this is it. This is the resultant vector of all 4 of those vectors being added. Now, a nice little trick that we can see here, because these vectors can also be represented in terms of their endpoints. If I add vector AB plus BC, because it's arranged head to tail, the resultant is just AC. And if you look here, even looking at the equation itself, or the letters, you can see the head is lined up with the tail because the B's are beside each other to get this resultant. Then when I add AC with CD, again, I notice that the C's are head to tail. So the sum should be AD, which is exactly what we get. AC plus CD is that AD. Then again, the D's are nicely lined up, so the sum must be AE. So AD plus AE is in fact AE. So that's a nice little trick we can use if we don't have a diagram to deal with, or if we like this manipulation better than the visual itself. So let's take a look at our next example. We have a rectangular prism, and for each of these questions, we have to create a single vector to equal the sum. So first we need to do AD plus DH. First of all, without even looking at my diagram, I see that the vectors are arranged head to tail. So I already know that this is going to be vector AH. But visually, here's vector AD, here's vector DH. There's that head to tail, so we're using the triangle law. So we have to start at the tail of A and end at the head of H. Next we have vector AE plus vector HC. These vectors are not arranged head to tail, so I need to go to my diagram. Here's vector AE, and I also need vector HC. Now I can use my knowledge of equal vectors to come up with an equal vector to either AE or HC to then find my resultant vector. Well, vector HC is equal to vector EB. So I can write that out if I want to, or I could just use the visual. And now I can see that we're arranged head to tail, so the vector must be AB, which my visual would also show. Next, we have 3 vectors that we're adding. AB plus BF plus FG. Without even looking at my diagram first, I can see that all my vectors are lined up head to tail. The head of B with the tail of B. The head of F with the tail of F. So just looking at this, I'm already thinking that the vector will be AG. But let's take a look at our diagram. AB plus BF plus FG. Using that commutative property, if all of our vectors are lined up head to tail, we can just start at the tail of A and end at the head of G. And that's our resultant vector. Next we have AD plus AE plus AB. Well, all of these vectors seem to start from A. So let's take a look. They're not arranged head to tail, so I can't use that commutative property. I have AD going like this, I have AE going like this, and AB going like this. Now there's different ways we can do this. One way is to find equal vectors so that all of my vectors are lined up head to tail, and then I can use that commutative property. So for example, I'll keep AD the way it is, but vector AE, I can instead write it as DH. So AD keep, AE is now DH because they're equal vectors, and instead of AB, I can do HG. Now everyone is lined up head to tail, and my resultant vector will start at A and end at G. And there we are. Another way would be a little more visual. So I can actually do the sum, find the resultant vector one by one using the parallelogram law. So for example, if I did AD plus AE, because the vectors are lined up tail to tail, I can use the parallelogram law. So their sum is AH. And then I can do AH plus AB. Now here I have to think a little bit more in the 3D space to create my parallelogram. The parallelogram, first of all, parallel to AH would be BG, and then parallel to AB would be HG. So there's the parallelogram. And then we're starting at the tails and ending at the diagonal. So we still get AG, just a more visual approach. Either way, it's perfectly fine. So now we can move on to subtracting vectors. So again, we have different ways we can approach subtracting vectors. One way is to think of it as addition. Instead of me doing A minus B, I can add A with the opposite vector of B. So I can do A plus negative B. So let's say vector B had been this vector here. Okay, instead of doing A plus B, I can take the opposite vector of B, which is now this one here, and I'm doing A plus this opposite vector. And these vectors are lined up head to tail, so here is my resultant vector. So I can think about it as addition with an opposite vector. Another way, if you look at these vectors here to try to come up with another strategy is, well, what would it look like if I lined my vectors up tail to tail? So here, vectors A and B are tail to tail, and I know that the resultant vector should be this, which is this vector here. Now, how could we get it when we're arranged tail to tail? If I'm doing A minus B, I'm going to start at the head of my second vector and go up to my first vector. So here it's a head to head. The resultant vector is from the head of one to the head of the other, but that's only for subtraction. So let's try this out visually. I have two vectors, A and V, and in each scenario I want to find A minus V. So in our first one, our vectors are lined up tail to tail. So I'm going to use that triangle law where I'm going to go from the head of one to the head of the other. Because I'm doing U minus V, I have to start at my second vector. So I'm going to start at V and head towards U. And this is our subtracted vector. And the next one, we're lined up head to tail. So here I'm thinking, you know what, I'm going to use that subtracting by adding an opposite vector. So I'm doing U minus V. So I'm going to take the opposite of vector V. So I'm going to keep its direction, or I'm going to keep its overall shape, but I'm going to go in the opposite direction. So this is the opposite vector. They're lined up head to tail. So my resultant vector, because it's the sum of these two vectors, would be this right here. Now, if you like a particular method better, you could always rearrange your vectors to make it work. For example, if for subtraction I really like doing the tail to tail method, I could always take vector V and shimmy it over like this. And now I'm tail to tail with U and V, and my resultant vector is going to start from V and end to U. And you'll notice that the two resultant vectors I drew, they're the exact same. They are equal. So you can always shimmy your vectors around to use your preferred method. Okay, let's add in a few vectors here. So I have 3 vectors and I want us to arrange them so that we can sketch vector A minus vector B plus vector C. And there's different ways you can do this. We can turn this all in terms of addition. So I can do vector A plus opposite vector B plus vector C, line them up head to tail, and use that commutative property. So here's vector A. I want to add the opposite vector to B. And just looking at your sketch of the vectors at the beginning, vector B is shorter. I'm just going to change its direction. And then we're adding vector C, which is something like this. So my resultant should be this. That's one way. To me, this is the most direct way, fewest steps, but of course we can also take it one operation at a time and keep the operations as is. So for example, I could also do, here's vector A, here's vector B, and I need to do A minus B, so I'll draw that in. Start at B, go to A, there's A minus B, and now I can add on vector C. And my resultant vector, it's gonna be the same thing. Just took a few more steps. So lots of different ways to do the same thing. Okay, ABCD is a square. Express each difference as a single vector. We could do this visually, or we can manipulate our vectors. I really like that commutative property. I would like to set all of these up so that they're the sum of vectors and have them arranged nicely head to tail. So first thing I'm going to do, if I want to turn this into addition, I can always turn BA into its opposite vector. So instead of BA, I can write negative AB. And we know 2 negatives make a positive. Okay, that's great, it's addition. And look at this, these are both B's. I'm just gonna swap my vectors around because I know I can add vectors in whatever order I would like. And now I've arranged them head to tail. So my resultant is AC. Now that's a more algebraic approach, but I can also just draw my square. A, B, C, D. We wanted to do vector BC minus vector BA. We start at our second vector and go to our first. Same thing, vector AC. Let's try the next one. AC minus BC. I'll show both ways again. I'm going to manipulate BC into its opposite vector, which is negative CB. That turns this to addition. My vectors are already arranged head to tail right here, so I know my vector should be AB. Visually, what does this look like? Okay, vector AC is the one in red minus vector BC. Now, I'm going to arrange these in a head to or a tail to tail. So I'm going to get an equivalent vector right here. And if I were to subtract AC minus, well, now it's minus AD, this should be my vector. So DC would be another option, but we know DC is equivalent to AB. So there are 2 answers in this scenario. And let's do one more visual example. So we have a rectangular box here, and we're told that from O to A is vector A, from O to C is vector B, and from O to D is vector C. And we have to express each of these in terms of vectors A, B, and C. So let's get started. First we have vector BF. Well, that is just equal to vector C. They have the same magnitude, same direction. Then we have vector ED. Right here, same magnitude as vector A, parallel to it but opposite direction. So that's equivalent to vector negative A. Next we have OB right over here. Now this looks like something related to vector A and B. A and B are tail to tail, and this resultant vector is the diagonal of that base rectangle. So this must be the sum of A and B. Next we have vector AC, so the other diagonal. Now again, the vectors are tail to tail for A and B, but now our resultant vector is from the heads of vectors A and B. So this must be a subtraction. It started at vector A and ended at vector B, so we must be subtracting vector A from B. So B minus A. Next we have vector BG. So right here. So that's going to involve vector C and vector A. So I'm just going to go in and redraw vector C, something parallel to it or equivalent to it. So this here is also vector C, and this here is vector A. Or if we change the direction, this is vector negative A, and this is vector C. So it's the sum of vector C and the opposite vector of A. There we are. And finally, vector OF is this right here, and that looks like the sum from O to B and B to F. Well, B to F is just equivalent to vector C, and vector OB we've already established is the sum of A and B. So OF is the sum of all three vectors. Next, scalar multiplication. If you repeatedly add the same vector with itself, you're just making a vector that has a bigger magnitude but same overall direction, or it could be in the opposite direction if we're subtracting it. But instead of repeatedly adding this vector, we can just use multiplication. So if I have vector A added 3 times, I can just write 3 times vector A. And if I have B 2 times, I can just write 2 times vector B. And when you multiply a vector by a scalar, it will change the magnitude of the vector, and this new vector will be parallel, and it could go in the same direction if that scalar value is greater than 0, but if it's less than 0, we're now going to go in the opposite direction. Okay. And when one vector is a scalar multiple of another, and the two vectors are parallel, we call these vectors collinear. So for example, if this is vector A, and I want vector 3 times A, there's 1, there's 2, there's 3 of them. These are collinear. They're parallel to each other. The magnitudes aren't the same, but they are parallel. Or let's say I had negative 1/2 times vector A. So I want half the magnitude and then just going in the opposite direction. All 3 of these are collinear because they're all parallel to each other. If I were to take one and put it on top of the other, they would line up nicely. All right, another visual example here. In rectangle ABCD, X and Y are the midpoints. So right here, these are midpoints, meaning AX and XB are the same, AY and YD are the same. And then we're told that vector A is from A to X and vector B is from A to Y. And we need to express each of these vectors as in terms of A and B, or both. So we'll start with vector AB. Well, vector AB is just 2 of the vector A's. Vector DA, So it's 2 vector b's, but going in the opposite direction. So negative 2 times vector b. X, y. From x to y is this. Now you'll notice that this resultant vector is from the head of A to the head of B, so this must be subtraction. We're starting at A, so we must be subtracting vector A. Next we have YC, which is this vector here, and it is the resultant vector of this with this. Now this horizontal one, that's just 2 of the vector A's because it's parallel to AB and the same magnitude, and this is vector B. So 2 A's plus vector B. Next I have from X to C, well, that's 1 vector A and 2 vector B's, and it is the sum because those vectors are arranged head to tail. And finally, BD. BD is this right here. So it is coming off of 2 A's and 2 B's. We're starting at the head of the double vector A, so that's what we must be subtracting. So 2 times vector B minus 2 times vector A. So just being careful with how are the vectors positioned. Are they tail to tail or head to tail to decide on addition or subtraction? Look at what vectors are equivalent or parallel to each other. And when you can write a vector as a combination of another 2 or 3, this is called a linear combination. And final example here, I have a trapezoid. We're told that OA is vector U, OD is vector V, and we need to express each of these as a linear combination of U and V. So we're going to start with OC, this vector here. Well, my vectors are positioned tail to tail, U and V, and vector OC is just the diagonal of the parallelogram formed between vectors U and V. So this is just a sum of U and V. Next we have vector AB. Well, vector AB is equal to vector OC. They're the same magnitude, they're parallel, same direction, which means that AB must also be the sum of U and V. Next, we're going to look from O to B. Well, vector OB is the sum of vector U and vector AB, but we've already established that vector AB is U plus V. So I'm adding U with U plus V, that's 2 U's and 1 V. And finally, we have vector AD. This is coming from the head of U to the head of V, so this must be subtraction. And since I started at vector U, that must be the vector that I'm subtracting. So that's it for our vector addition and subtraction. As I said, the key is looking at how your vectors are arranged. Are they head to tail? Are they tail to tail? Is it addition? Is it subtraction? Where is the resultant vector starting, to make sure you get the correct combination and the correct visualization.